Hello everyone, I'm SJBIT, working as Assistant Professor in the Department of PC SJBIT. In this lecture, we'll be discussing about computer organization and architecture.
First topic, what is a basic processing unit? So here we know that a common strategy in the development of high performance processor is to make various fundamental units operations operate in parallel as much as possible. So the all the work should be execute parallelly because wasting the CPU time does not speed up the operation. For that reason, we work as much as parallel possible. So high performance processor have pipelined organization where the execution of one instruction is started before the execution of preceding instruction is completed. So for this, we can give the example of the program counter. So program counter is going to give always it is going to point out which is the instruction to be executed next, whereas instruction register which is going to give the instruction current it is current instruction which is to be executed. So another approach for this, it is known as a superscalar operation. So several instructions are fetched and executed at the same time. So what is pipelining? Pipelining is nothing but queuing. Okay, pipelining and the superscalar architecture, which is to be discussed later. So this is the typical computing task consisting of series of steps specified by the sequence of machine instructions that constitute a program. Okay, so we have, you know that there are the three level of coding. One is the machine level coding, the other one is the assembly level coding, and the third one is the high level coding. So we use the program C, C++, Java and all are the considered as the high level coding. You give the instructions, you are going to type in the form of English alphabets. When you come to the assembly level, it is only a alphabet contains we are going to type, and the machine level, you know that these are going to be considered in form of zeros and ones. So these are known as the machine level instructions. So to execute a program, the processor fetches one instruction at a time. So and perform the operation specified. Whenever the instruction is fetched from the successive memory location until a branch or a jump instruction is encountered. Okay, the processor keeps track of the address of the memory location containing the next instruction to be fetched using the program counter. So after fetching an instruction, the content of the PC is updated to a point to the next instruction in the sequence. So a branch instruction may load to a different value into the PC. So another key register that processor is the instruction register. Okay, so before discussing on the instruction register, so an overview of instruction set processor and control processing unit. What is instruction set processor? A typical computing task consisting of a series of steps specified by the sequence of machine instructions that constitute a program, that is known as the instruction set processor. Next one is the instruction is executed by carry out a sequence of more rudimentary operations. Okay, some fundamental concept, that is what I was discussing earlier. What is the processor does? The processor fetches one instruction at a time and perform the operation being specified. If it is add to multiply, so that operation is going to be done under the ALU consideration. So an instructions are fetched from the successive memory location until a branch or a jump instruction is encountered. So a sequence, if it is executing flow, is going to be the instruction execution which encounter a branch instruction, which is another instruction will take the part of the program to the another memory address. So that is known as the memory location until a branch or a jump instruction is encountered. The processor keeps track of address of the memory location containing the next instruction to be fetched using the program counter and instruction register. So symbolically, so what is an execution of instruction? So executing an instruction, fetch the contents of the memory location pointed to by the program counter. The content of the locations are loaded into the instruction register, that is the fetch phase. The current instruction to be executed, that is going to move to the instruction register. So assuming that the memory is byte addressable, the increment content of the PC by 4. So why this is 4 is required here? The 4 is indicating the addressing scheme of the processor, whether it is a 32-bit, 64-bit or the 128. So this is nothing but the 32-bit addressing mode. That is nothing but 2 to the power of 4 is nothing but the 32. So for that reason, so it is getting incremented by 4 times. So that is what, assuming that the memory is a byte addressable, increment the content of the program counter by 4 and carry out the action specified by the instruction in the instruction register. Okay. So these are the three steps to be followed to fetching the instruction from the memory. So in this case, where an instruction occupies more than one word, if it is going to occupy more than one word, the step one and must be required as many times memory necessary to fetch the memory content to complete the instruction. So the earlier steps what we discussed, that is the fetch the content of the memory location pointed by the PC. That is the fetching is done by using the processor, and that is going to be stored in the instruction register. The content of that particular memory location is being stored in the instruction register. This keeps on repeating if the instruction occupies more than one word. The step one and must be repeated many times as necessary to fetch the complete instruction. So these two steps are usually referred as the fetch phase. And the step 3, that is carry out the action specified by the instruction register in the IR, that is considered as the execution phase. So the main building block of the processor are introduced in this figure as shown in the figure, that is this can be organized and interconnected in a variety of ways. So let us start discussing on this, the operation of the execution of instruction. So you are able to see the program counter, memory address register, MDR, Y, and the constant 4. This is to increment the program counter 5 at the 4 bytes, and the ALU register will contain the arithmetic unit is going to be arithmetic and logic unit. ALU stands for arithmetic and the logic unit, contains two registers, that is A and B, and this is the Z register. The output of the ALU being given to the Z registers. So these are the control signals being used, that is the instruction decoder and the control logic. So from the whatever the fetch current instruction been given to the instruction decoder, because only it is in the coded form, so that has to be converted into a machine level language, and that is done by using the instruction decoder. And this is known as the general purpose register, that is R0 to Rn-1, and this is the temporary storage area. Okay, let us discuss one by one among this. So first, the data and address of the external memory bus as shown in the figure 7.1. Okay, so these are all externally connected. These two lines are going to be considered as the external memory bus content to the internal processor via the memory data register. So the content is going to be copied to the memory data register, and the address being located by the memory address register. Okay, so the MDR has two inputs and the two outputs. So here you are able to see MDR is going to be connected to the internal CPU bus, as well as it being connected to the external to the memory bus. Okay. Data may be loaded into MDR either form of the memory bus or from the external processor bus. So the data is stored. It is the data which is being fetched from the external memory being stored in the MDR, may be placed either the bus. So the input of MER is going to be connected to the internal bus. The MER is going to be connected to the internal bus here. So its output is connected to the external bus, and the control lines of the memory bus are connected to the instruction decoder. So here you are able to see the instruction decoder is going to be connected to the external processor bus here. So the control lines of the memory bus are connected to the instruction decoder and control logic bank. So this unit is responsible. This unit is responsible for issuing the control signals for the operation sake. So the which is the processor inside the processor and for interacting with the memory bus. This is going to intimate the processor to be interact with the external medium, that is the memory, or to the internal medium within the processor. So the number of use of processor registers, so these are all known as the registers, that is R0 to Rn-1 vary considerably from one processor to another processor. So here it is Rn-1, this depends on the memory capacity of the processor. So some may dedicated as a special purpose register such as the index register and the stack pointer. There are three registers you are able to see, that is Y, Z and temp as shown in the figure. These registers are transparent to the programmer. That is the programmer need to connect with them because they never reference to the explicit instruction. These are all A, B, Z and temporary register within the processor. Only the processor or execution of the program is going to be utilize these register to store the data temporarily. So for example, if addition add 2 3 numbers, so add and result will be stored in this Z register or the temporary register or the processor register, that is R1 to Rn minus 1. Okay, the multiplexer here you are able to see, this is a multiplexer, selects either the output of the register Y or a constant value of 4. When this is the constant value being selected, that is nothing but the program counter is going to be incremented by 4. So the Y, if it is Y being selected, that is the data being copied from the memory to the ALU. Okay, so Y is selecting the constant, this multiplexer is going to be used to select the constant Y or the constant 4, either one of the input being provided to the multiplexer. Okay, so as an instruction execution process, the data are transferred from one register to another register. While often passing through the ALU performs some arithmetic and logic operation, the instruction decoder and the control unit is responsible for implementing the actions specified by the instruction loaded in the IR register. So the decoder generates the control signal needed to select the register involved and direct transfer of data. And so the decoder, what the decoder does, it is going to generate the control signals, whether the data to be read or the write, or to read from the external bus or to write into the external bus, or to take the data from the MDR, or the data to be moved to the Y, that and all to be considered by this, controlled by this instruction decoder and the control logic. Okay, what the decoder does, the decoder is going to generate the control signal, need to select the register involved and direct the transfer data. So the register ALU and the interconnecting bus are collectively referred as the data path. So this is what ALU, the registers, ALU and interconnecting bus is collectively referred as the data path. So with a few exception, an instruction can be executed by performing one or more the following operations in some specified sequence. Transfer a word of data from one processor register to another to the ALU. So what it does, it is going to transfer the word of data from one register. So this can be R1, add R1, R2, R3. The add and result should be moved to the R3. So during that time, transfer a word of data from one processor register to another or to the ALU. So perform the arithmetic operation, arithmetic or the logical operation, and store the result in the processor register. Fetch the content of a given memory location and load into a processor register. Fetch the content of the given memory location, load into the processor register. To store a word of data from the processor register to a given memory location. So these are the operation is going to be executed by this unit. Okay, so as shown in the figure, first let me consider the what is the register transfers. So here in this, so that is what, transfer a word of data from one register to the another, perform an arithmetic and logic operation and store the result in a processor register, fetch the content of the given memory location and load them into a processor register, and store the word from the processor register into a given memory location. Okay, so this is the diagram which has been depicting as the register transfer flow. So what happens in the register transfer flow? The instruction execution that involves the sequence of steps in which the data are transferred from one register to the another. For each register, for each of the register, it is going to generate two control signals are used. One is RI is the nothing but the connected to the bus via the switches controlled by. So you are able to see each register being connected to the processor bus. Let me take one of the register which is going to have connect through a switch, that is REN, and RI out being given to the register RI. What is REN? REN is when REN 2 respectively, when REN is set is equal to 1, when this switch is going to be active. So during that time data on the bus are loaded to RI. When this is going to be is equal to 1, the data from register being connected to the internal internal processor bus. Okay, so suppose we wish to transfer the content of register within the register transfer, that is R1 to register R4. What are the steps to be followed? First step is to be enable output of the register R1 by setting which signal R1 out is equal to 1. This places the content of R1 to the processor internal bus. So enable the register R4 as R4 into 1. This loads the data from the processor into the register R4. So all the operations and the data transfer within the processor takes place within the time period. It is known as the processor clock. So the control signals that govern a particular transfer asserted at the start of the clock cycle. So in our example we have considered, that is the R1 out and R4 in are set to be is equal to 1. So these registers are considered. These registers are going to be edge triggered flip-flops. So flip-flops we know which is going to store 1 bit at a time. So it is a collection of flip-flop. If I specify it as a 32-bit register, this is a collection of flip-flops which is going to have the 32 flip-flops that time. So hence the next active edge of the clock, the flip-flop, that is R4, will load to the data present their input. So at this same time the control signals R1 out and R4 in will return to 0. So after transferring the content of R1 to the processor bus, and that is being copied to the R4, the type that is since it is executable, the control signal of R1 out is equal to 0 and R4 in is equal to 0. So it is going to point out the other scheme. So for example, data transfer may use both the rising and the falling edge of the clock, and also when edge triggered flip-flops are not used, 2 or more clock signals may be needed to guarantee the proper transfer data. This particular concept, it is known as the multi-phase clocking. As we discussed about only the edge triggering flip-flops, so it may use the other type of the clocking signals also other than the edge triggered. So 2 or more clock signals may need to guarantee the proper transfer of data, and that is known as the multi-phase clocking. So an implementation for 1 bit of register RI as shown in the figure. So this is what as shown in the figure. So this is going to give a 1 bit transfer of information. Okay. So a 2 input multiplexer. Here you are able to see 2 input multiplexer will be given to the constant values of R1, 1 and 0. So one of the input depending on the RN, this is going to be enabled, whether it is reading from the bus or be transferred data to the RI out. So depending on this, when RI out is equal to 1, this signal is equal to 1. So that is nothing but 0 means it is going to be read. 0 means it is going to be internal register communication. Okay. So 1 is nothing but it is being connected to the external. So REN1 is equal to nothing but it has to data to be collected from the external bus. So when REN is equal to 0 is nothing but the data to be transferred to the buffer register which is RI out. So here you are able to see that 2 input multiplexer is used to select the data applied to the input of the edge triggered D flip flop. So D flip flop, you know, it is the data D stands for data. Okay, so it is going to follow the input. It is going to follow the input. Whatever the input you are going to provide, that is the input is going to be followed. So when the control input REN is equal to 1, REN is equal to 1, the multiplexer select the data on the bus. The multiplexer is going to select the data on the bus, and this data will be loaded into the flip-flop at the rising edge of the clock. when Rn is equal to 0, multiplexer feeds back the value of currently being stored in the flip-flop. So it is going to feed back the program currently being stored. What is the currently being stored? That is going to be given to the Ri out. The Q output of the flip-flop is connected to the bus via the tri-state gate. So here you are able to see that this is going to be a tri-state gate, which is Ri out is equal to 0 and the gate is output. Output is in the high impedance. This corresponds to the open state of the switch. When Ri out is equal to 1, the gate drives the bus is equal to 0 or 1 depending on the value of Q. So this is going to be 0 on that, this is going to be defining as the tri-state high impedance state. When this is going to be 1, the data being given to the bus. This is how it is going to operate. So this is about this video is regarding about the digital transfer and some fundamental concepts of the execution of instructions. Thank you.